Hello, my name is Cyrus Silic, and today I'll be talking about our work making congestion control algorithms insensitive to underlying propagation delays. Congestion control algorithms manage the sending rates of network end hosts to prevent congestion collapse and to control how available capacity is shared between competing streams of traffic. The original mechanism was proposed back in 1988, and since then, as the internet has increased in available capacity and in the number of users, today there are many different congestion control algorithms, some of which are designed for different network settings, for example, in data centers or over wide area networks, and some of which are designed for different performance objectives, for example, achieving lower latency or higher utilization. The way that congestion control algorithms manage the rates of competing streams of traffic depends on the network settings these streams of traffic are in. For example, in this scenario, there are three users simultaneously requesting data from the internet while sharing a 50 megabit per second bottleneck. The way that the rates are allocated will depend on the properties of the shared bottleneck and on the number of competing flows. And it's also going to depend on the respective applications and their relative throughput needs to achieve a good quality of experience. In settings where the applications have different workloads and choose to utilize different CCAs, the difference in their respective CCAs will also impact the relative rates that they achieve. The way that different CCAs should compete depends on your stance on internet fairness. But the reality today is that many applications choose to use the CCA that best suits their own needs rather than the CCAs that are the most fair. In this talk, we're not taking a strong stance on the importance or definition of internet fairness, but instead are proposing a more broadly acceptable notion of predictability, in that ideally, the rates allocated to a set of competing applications should be predictable as a function of the decisions made by the applications and the property of the bottleneck that they share. And it should not depend on any extraneous network factors. And in particular for this talk is the network factor of end-to-end propagation delay. As a refresher, propagation delay is the minimum achievable round trip time, which is the minimum time it takes for a packet to go from the sender to the receiver and for the acknowledgement of that packet to return to the sender. We view propagation delay as an extraneous factor because it cannot be altered by the end host, which is different from congestive delay or queuing delay, which will depend on the properties of the bottleneck and on the aggressiveness of the CCAs that the applications choose to utilize. When CCAs are sensitive to propagation delay, then performance of a set of applications sharing a bottleneck is unpredictable because the allocation of rates will vary as we vary propagation delays. If instead CCAs are insensitive to propagation delays, then performance is predictable because the allocation of rates between a set of applications will be met more consistently across network settings with varied propagation delays. It is well known that the most popular CCAs used today are sensitive to propagation delay. Competing flows utilizing cubic will converge such that the shorter delayed flow will achieve a larger share of bandwidth. And BBR has the reverse property where the larger delayed flow will converge to a larger share of bandwidth. There are some CCAs which are designed to converge to delay insensitive rates, in that provided that all of the competing flows utilize that same CCA, they will converge to equal rates regardless of their respective propagation delays. However, this requires that all competing flows utilize that same CCA, and in settings where they compete with a flow which utilizes a different CCA, the flows can again become sensitive to their propagation delays. And it remains the case that most applications will use popular CCAs such as BBR and Cubic, which can achieve larger rates in these heterogeneous settings. Another issue is that there is not a clear way to measure the impact of propagation delay when competing flows are heterogeneous. Here we have two competing flows which are using different CCAs and have different propagation delays. If we compare the rates allocated to the competing flows, it is unclear what aspect is a result of the difference in their utilized CCA and what is a result of the difference in their propagation delay. We also can't rely on what we know about CCAs in homogeneous settings to inform us of what will happen in heterogeneous cases. For example, here we have a cubic flow competing against a BBR flow where both have 12 milliseconds of propagation delay. In this case, the cubic flow converges to a rate of 25 megabits per second. If we increase the propagation delay of the cubic flow, we observe that its allocated rate actually increases, which contradicts what we might expect from homogeneous settings where the shorter delayed cubic flow achieves a larger rate. So we want to be able to measure how variations in propagation rate impacts performance in heterogeneous settings without having to compare the rates between competing applications that might have different workloads and throughput needs, or relying on what we know in settings where competing flows use the same CCA. Really, what we want is some way to quantify this notion of predictability with respect to the possible propagation delays that competing applications might have. To do this, we can focus on each flow individually and observe the rate this flow achieves across different network settings where the competing applications have different propagation delays. And then we can measure predictability with respect to the range of propagation delays that occur between these competing applications. The reason to consider sensitivity with respect to a range of propagation delays is that different network settings might have different plausible ranges for what delays will naturally occur. For example, the range of propagation delays encountered in data centers will have much less variability than those encountered in wide area networks. It's also possible that different flows in the mix will have different ranges of delay. Like when content from a CDN node, which has relatively low propagation delays, competes with flows where the range of delays varies in a much larger range. Formally, to quantify delay sensitivity, we fix the set of competing applications and the properties of the shared bottleneck, and then we measure rate variability over a defined range of possible propagation delay configurations. And we measure sensitivity to delay as the log ratio between the largest and smallest rate over this specified range of delays for each flow. In this figure, we show the sensitivity of the first BBR flow as it competes against another BBR flow in different ranges of delay, where we vary the minimum delay of the range on the x-axis and the maximum delay of the range on the y-axis. Then we can consider the sensitivity of the BBR flow when the range of delay falls between 16 and 48 milliseconds, and we can see how this sensitivity is different than if the propagation delays of both flows are between 8 and 16 milliseconds. Currently, real-world applications are sensitive to practical ranges of propagation delay. Here we are showing the time a 4K YouTube video stalls when sharing a 50 megabit per second bottleneck with a OneDrive file download, where we repeat this over 3 trials where the YouTube flow has 37 milliseconds of propagation delay and the OneDrive flow has 12 milliseconds of propagation delay. And we observed that the stall time of the YouTube video increases a lot when the propagation delays are switched, where the YouTube video has 12 milliseconds of propagation delay and the OneDrive file download has 37 milliseconds of propagation delay. Instead of focusing on specific configurations of propagation delay, we should quantify the sensitivity over the full range of practical propagation delays. In this figure, we plot the sensitivity of application 1, which is shown on the left of the figure, when it competes against application 2, which is shown above, in the range of propagation delays between 7 and 37 milliseconds. The significance of this sensitivity means that the performance of these competing applications will vary based on the propagation delays and will be unpredictable as just a function of the needs and decisions made by these applications. Our goal is to reduce how sensitive CCAs are to the range of propagation delays that are practical in the network setting that they operate in. And we want to do this without requiring new adjustments in the CCA's control loop or requiring that all flows utilize the same CCA. Our simple idea is that if all flows agree on some propagation delay lambda that is larger than the delays which occur naturally in their network settings, then if each flow artificially adds delay to alter how the network path is perceived by the CCA, then no matter what CCAs are in use and what natural propagation delays competing flows have, the CCAs will operate as if they have this larger propagation delay lambda. So we can trick a CCA into thinking it is operating with a larger propagation delay by delaying the sending or receiving of packets at either the sender or the receiver. But we have to be careful not to add delay on application data between sending a data packet from the sender and receiving it at the receiver, so we can preserve the actual data latency. But if we add delay by delaying the processing of packet acknowledgements at the sender, by holding them for a fixed amount of time before releasing them to the CCA to be processed, then we can artificially increase delay without adding data latency. In this figure, we are plotting the impact of adding 60 milliseconds of artificial delay in the 4 possible locations. And we see that as long as we are adding delay on the acknowledgement path, then the data latency is preserved, but the total minimum round trip time is increased. It's also important that we're equalizing propagation delay and not full round trip time. This way, CCAs such as BBR, which use variations in congestive delay as a congestion signal, can still operate normally with this larger perceived propagation delay. To equalize propagation delay, we have to make an estimate of the naturally occurring propagation delay. And this is a relatively easy measure to make because estimating propagation delay is just a measure of the minimum round trip time observed. And many CCAs, such as BBR, have specific mechanisms built in that periodically reduce sending rate to drain the queue, which makes it easier to gain an accurate estimate of the natural propagation delay. In these figures, we are showing how implementing this added delay solution, where we choose 100 milliseconds as the equalization point, is able to reduce the sensitivity to practically zero for both version 1 and version 3 of BBR. So when we add this artificial delay to the processing of acknowledgements, we are delaying the rate at which a CCA is able to respond to congestion feedback. We want the benefit of equalizing delay when applications compete, but we only want to do this in settings where adding this delay is not going to negatively impact performance when the application is operating alone. The way that adding delay will impact performance is the same as if the CCA was naturally operating with this larger inflated delay. And generally speaking, the performance of long-lived application workloads will not be hurt by just having a larger propagation delay. For example, a file download will take practically the same time when operating in an uncontested network with 10 milliseconds of propagation delay as it would with 100 milliseconds of propagation delay. However, with short-lived flows like web browsing, the increase in propagation delay could impact performance, and also short-lived flows do not last long enough to adapt to congestion signals and converge to rates. And the purpose of equalizing delay is for long-lived flows which do last long enough to respond to congestion signals when competing with one another. So far, we have been discussing using artificial delay to equalize propagation delay between competing flows. The benefits of this solution is that it removes the negative impact of sensitivity that occurs in the natural range of propagation delays that a flow operates in. We can reduce sensitivity in even simpler ways by using artificial delay to just change or reduce the possible range of delays. For example, in this figure, we are comparing the sensitivity of 4 competing flows utilizing 4 different CCAs when their propagation delay range is between 10 and 30 milliseconds, and when we add 50 milliseconds of fixed artificial delay to all flows, regardless of what their natural propagation delays are, to inflate the effective range of propagation delays to being between 60 and 80 milliseconds. And just by changing the range of delays, we have reduced the sensitivity delay between these competing flows in this setting. Finally, it's important to note that even when there are errors when we are trying to equalize propagation delay, then as long as we are reducing the range of propagation delay, the sensitivity to delay is still reduced. In this figure, we are plotting the sensitivity of 4 competing loss-based CCAs in the range of delays between 10 and 30 milliseconds. And we're comparing this to the sensitivity to the altered range, where delays are inflated to being between 35 and 45 milliseconds. Just by reducing the range from a 20 millisecond range between 10 and 30 milliseconds just to a 10 millisecond range between 35 and 45 milliseconds, the sensitivity of all of the competing flows is reduced. In summary, we showed that both measuring and addressing the impact of propagation delay is difficult in heterogeneous settings, and we proposed delay sensitivity as a way to quantify this notion of predictability with respect to the ranges of propagation delay that are practical to real-world settings. And we proposed a simple solution of using artificial delay to reduce the sensitivity to propagation delay. So measuring delay sensitivity by the practical range of propagation delays that are encountered could be useful when designing new CCAs, where the design could be geared specifically towards the practical range of delays. And if competing flows could agree on some equalization point lambda, then CCAs could be optimized to perform at that specific point of equalization. It's also interesting to think about how one could choose an optimal equalization point lambda. There could be benefits from choosing a lambda that is large enough to capture the bulk of competing flows while not having to be larger than any possible propagation delay. And this is because even just by reducing the total range of propagation delays, real-world sensitivity should reduce. In this work, we considered the use of artificial delay as a method to reduce the negative impact of propagation delay variation. But in future work, other, hopefully less controversial methods could focus on reducing delay sensitivity without introducing added artificial delay. Thank you.